Hello, Tanya Laird here, and welcome to part 2 of Lecture 12 of ENGR 231 Engineering Statics. In this portion of the lecture, I'm going to work through a few basic examples of finding internal forces in members. So I'm going to start with something very simple first, and that would be just a basic, simply supported beam. And maybe I can start with something even simpler than just a basic beam with just some point loads on it. So say something like this. And let's say that I have maybe a 10 kip load here, and then at, actually, maybe I'll do something like this. Maybe I'll put it at an angle. So that way I can get some axial force in there. So let's say I have a 10 kip force here, and this is at an angle of 30 degrees. So you have a 10 kip force at an angle of 30 degrees. And let's give us some distances here. Or let's provide some distances. And I'm going to be looking at the internal forces at this point here. That's my goal. And let's say I have this point, maybe this is point A where the force is applied, and maybe this is point B. And then let's give this some dimensions of maybe, I don't know, maybe 6 feet, 6 feet, and 6 feet. Something like this. So all this is given. And I want to find the internal forces at point B. The internal forces at point B. Actually, looking at this, I think I might switch this around a little bit. And I think it might make a little more sense to do the internal force at point A here. That'll be a bit more interesting on the axial force front. So let's go ahead and look at that. I think that'll work out a little bit better. So you have a 10 kip force again at an angle of 30 degrees. Okay, so we're going to find the internal forces at point A. And then solution. So the first step is going to be to look at this from a global perspective and find the external reaction forces. So step 1, find the external reaction forces if possible. For simple beams, that's usually going to be the case, but for more complex frames, as we saw in the last unit, or in the last video, or in the last lecture, I should say, sometimes it's not possible to find all of the internal forces, or all of the external forces, just by treating the whole thing as a single rigid body. Find the external reactions if possible. So this is a simply supported beam, so really not too bad. We're going to have a pin and a roller. So I'm going to go ahead and draw a free body diagram showing all of the external forces on the beam. Maybe I can call this, I already have points A and B here, so maybe I can call this end C and end D. So that's what I'll do for my forces here. I'm just going to call this end NC and this end ND. And then the forces here, I would have a CY and a CX. And then the 10 kip force here. Now I will go ahead and separate this into horizontal and vertical components. So I have, that's going to be 10 cosine 30, and then downward we'll have 10 sine 30. And then at point D we'll have a vertical force, and that will be dy, a vertical force of magnitude dy. So we'll have a vertical force which we'll call dy. And then I need to go ahead and label my dimensions. Now the point A, we don't need to include that dimension yet. We'll get to that when we do our cut. And so all I need is the dimension from here to here and from here to here. So this is going to be 12 feet and 6 feet. Let's make that a little bit neater. 12 feet and 6 feet. So the first thing I'm going to do is apply equations of equilibrium to this, and I think the first thing I'm going to do for this is a summation of forces in the x direction, and that will be, I'll have cx plus 10 cosine 30, and of course we know our basic trigonometry. We have a right and a 30, 60, 90. The cosine, and of course with this being 1, 2 square root of 3. So the cosine of 30 degrees is always going to be root 3 over 2. So, and this is equal to 0 because this is statics class. And cx then is going to be equal to negative 10 times root 3 over 2. Root 3 over 2, or just negative 5. Negative 5 root 3 kips. And I might just leave this in exact form for now. If it gets too bad or too ugly, I might end up switching to decimal mode. So basically we know we have Cx, the reaction force at point C, is going to be pulling the beam to the left, keeping it in equilibrium, canceling out the horizontal components of the horizontal component of this force here. Then summation of forces in the y direction. Well, I can't do that yet. I can't do that yet because I would have two forces, two unknowns in that equation, so that wouldn't necessarily work out. So instead, I'm going to do a summation of moments about point C. If I do a summation of moments about point C, I'll have first, now the two horizontal components and CY will not generate any moment there because they're lines of action, all pass through point C. But I will have this downward component and the dy. So I'll have negative 10 sine 30, because this is a negative, of course, because, and it's negative, of course, because it is clockwise rotation about point C, times a moment arm length of 12 feet, and then plus dy, positive rotation about point C, or counterclockwise or positive rotation, times a moment arm length of 18 feet, and all of this is equal to 0. And so then dy is going to be equal to, let's see, that's going to be, well, this is 1/2, and so that's basically negative 60. This is negative 60, but when I bring it over here, it's 60 over 18, I believe. So let me double check that. 10 times 0.5 times 12 divided by 18, and 60 divided by 18. And yep, 60 over 18, and let's see, what if I simplify that fraction, what is that? Let's see, that's 30 over, if I divide by 2, that's 30 over 9, or 10 over 3. 10 over 3 kips, and upward. 10/3 kips, and then I can just do a summation of moments in the, or about point D, to get my other reaction. And that's going to be 10 sine 30, which is a negative, which is a positive moment, but that's just negative 5. Negative 5 kips. Well, I guess I should say, sorry, that's a positive rotation about point D, so that should be positive. 5 kips times a moment arm length of 12 feet, or sorry, 6 feet, moment arm length of 6 feet, and then plus, or actually minus, of course, clockwise being negative, negative moment, negative cy times a moment arm length of 18 feet. And then all this comes to 0 because, of course, this is statics class. And then cy is going to be equal to 5 times 6 divided by 18. 5 times 6 divided by 18, or that would come to 5 over 3. 5 over 3, and when I add together, let's see, 5 over 3 and 10 over 3, those do come to 5 kips exactly, so it does check out in the summation of forces in the vertical direction. So 5/3 kips upward. Now, that's all well and good, and that's good, so we've made some progress, but all I've done is so far is solve for my external reactions. I have yet to actually solve for what I really want, which is the force at point A. And to do that, I'm going to create a free body diagram, a second free body diagram, and that is going to show a cut at point A. Maybe I'll draw it in a little different color. That will show the cut at point A and all of the forces that are revealed by that cut. So, just like we did with trusses, when we do this, when I'm going to cut this here, I'm going to cut this right about here, for example. And when I cut this, I'm going to show only the forces that are revealed and the forces on whatever side of the element that I want to consider. So if I want to analyze the left-hand side of this, which is what I'm going to do for this because that's a little simpler, I'm not going to need to draw the right-hand side of this, although I really could. In fact, you know what? Maybe let's just actually show what this would look like if I was going to draw both sides of it. So let's go ahead and draw this out. Let's first show what I would need to solve this problem. I would have, let's see, this is point C, and this is point A, and I'll probably should put a dimension on here. This is 6 feet, of course. Now, if I look at the types of forces that are applied to this, I have a horizontal force to the left of magnitude equal to negative root 5/3 kips, or just 5/3 kips to the 5 times root 3 kips to the right, or sorry, to the left. 5 root 3 kips here, and then I have an upward force equal to cy, which is, or I have an upward force of cy, which is equal to 5/3 kips, or 5/3 of a kip. 5/3 kips. Now, what type of forces are revealed at this cut? When I cut this thing at A, I'm going to reveal 3 internal forces. The first is an axial force, and just like I did with trusses, I'm going to generally assume everything is positive. So initially, I'm going to assume that my axial force is positive or in tension. I'm going to assume that my shear is positive and that my moment is positive. So if we go back to our sign convention discussion here, if we are on the right side of an element, positive shear has a downward arrow. So if I'm assuming positive for this, initially, again, if I get a negative number, that's fine, but I'm assuming positive initially. And so I have a downward arrow here on the right-hand side, and I'm assuming positive moment, a positive moment M. And often what I like to do when I'm doing method of sections like this, or I'm working with internal forces, I will often put a subscript on each of these to indicate what point that I'm actually making the cut at. So this is the free body diagram. This is actually a complete and fine free body diagram. But I would like to also show, for the sake of completion, like when working through a homework problem or something, I don't think you need to go beyond this, and I'm going to solve the rest of the problem using this. But for the sake of completion, let's look at what the other side would look like. Sometimes it is convenient to cut on the right-hand side of a cut, or not just cut on the right-hand side of the cut, but analyze to the right-hand side of a cut. And so if we looked at what forces are on this, I would have the dy here, which again was equal to 10/3. dy was equal to 10/3. I would have this, let's see, the 10 kip force at an angle of 30 degrees, and I could either draw that as one thing or as two. And then I would have the same internal forces, except they would be equal and opposite. So I'd have a normal force that would be stretching the member, but this time it would be going to the left, because it's also stretching. But another way to think of this is that Newton's third law, that if we apply Newton's third law, these arrows do have to be equal and opposite. And then shear, if this one's going down, this one must be going up. And notice, actually that should be called VA. And notice whether I look at this from the point of view of Newton's third law or not. That's why, even if I do that, if I say, well, if this one's going to be downward, then this one's going to have to be upward. Look at what happens when we go back to our sign convention for shear. Positive shear has a upward arrow on the right-hand side of an element, or a beam, or a piece of a beam, and look what we have. We have a positive arrow on the right-hand side of the element. And then MA would be, this time, going clockwise, even though this is positive. So this is where it gets particularly confusing, because this moment, even though it is clockwise, is positive because it's an internal moment on the right-hand side of a member, or the right-hand side of a section. So again, positive shear and positive moment depend not just on what direction the force is going, whether up or down or clockwise or counterclockwise, but they are based upon what kind of bending they are causing the member to experience. So for example, imagine this thing had its way and this thing was going to bend this member. This member would end up bending something like this. This force here, this MA here, would tend to cause this thing to bend like downward as well. So you can think about it that way. If any moment that is going to cause a beam for example, to bend downward, that is a positive moment. To get that, you need a clockwise moment on the right-hand side, or a counterclockwise, clockwise on the left-hand side, or a counterclockwise on the right-hand side. Anyway, then I guess for the sake of completion, I could put some dimensions on here. These would be 6 feet and 6 feet as well, per our original problem statement. So that would be 6 feet, and that would be 6 feet here. Now, the next thing I might do is I'm just going to analyze this one. You could use either one. Either one would give you the same results. Again, as long as we set everything up properly. And in fact, you might actually want to do that. If you want to check your knowledge, maybe go, after working through this one, maybe go and check your knowledge by working through this one and see if they produce the same results as what we're going to work through on this one. So I'm going to work through only equilibrium on this particular one, not on this one. And again, because we've cut this member, what is happening over in this section over here doesn't really matter. All that matters is the forces that are on the section that we are analyzing. So the first thing I can do is do a summation of forces in the x direction, and I will have negative 5 root 3 kips, of course, plus NA is equal to 0. And therefore, I get that NA is equal to 5 root 3 kips. And it's positive, so this is actually in tension. So we basically assumed right in this case. Next, I'm going to do a summation of forces in the horizontal direction, in the vertical direction. And I will have root 5 over 3, 5/3 kips, minus VA. Now, I know this can get very confusing very quickly. Where this is confusing now is that even though we do have positive state of shear here, when we apply a sum of forces in the vertical direction, we are now applying a global coordinate system. And so, or at least a local coordinate system. And so whether something is positive or negative, whether the state of shear is positive or negative, at the end of the day, the arrow is still pointing upward or downward. So when you're doing equilibrium like this, it doesn't matter whether, you can't just say, oh, it's positive shear, therefore put a plus VA in here. No, unfortunately, it isn't that simple. You actually have to look at then, just all that matters then is whether an individual arrow is pointing upward or downward. So I would have minus VA. And the moment would not contribute to the sum of forces. It only generates moment, or it only generates the translate to rotate, not the tendency to translate. And this then equals 0. And so if we solve this for VA, VA is equal to 5/3 kips. And so we actually did assume correctly we are in the state of positive shear. We did assume correctly. And then finally, I can do a sum of moments. And in terms of sum of moments, 9 times out of 10, it's going to be more convenient to sum moments about the point that you're cutting. And the nice thing about that is that I don't have to worry about the moment generated by VA. Now, for this type of simple method of sections, it's not going to be as important. But later, when we get to when we look at shear and moment functions, we're going to want to actually solve for some of these as functions of x. And in those cases, it would be very inconvenient to have to solve for have to include a function of x for your for one of your forces that you're taking moments of. And so I almost always, when I'm doing method of sections on beams to solve for internal forces, I almost always use the cut right at the point, take the sum of moments right at the location I'm doing the cut. Because then again, the only internal force that will generate any moment there is is the moment that's at the cut. So I'm going to do a summation of moments about point A. Again, the location of the cut. I'll have MA. And that's a positive moment, not because it's, again, not because I'm assuming this thing is in positive bending, but because this arrow is clockwise. The state of positive shear, positive moment depends on where things are on the beam, but when I'm doing equilibrium, all that matters is whether the arrows are up or down, or clockwise or counterclockwise. MA, and then the reaction force here and the NA do not generate any moment, so all that's left is the 5/3 kips here. And this is going to be a negative moment about point A because clockwise rotation. So minus 5/3 kips times a moment arm length of 6 feet. Moment arm length of 6 feet, and this equals 0. And therefore, MA is equal to, if I multiply that out, that simply reduces to 2. And so that's going to be equal to 10 kip feet. Simply 10 kip feet. And that's 10 kip feet. So hopefully not too bad. MA equals 10 kip feet. And we now actually have all of the internal forces at this cut. So if I were to draw out this cut again, what I would know is that there is a tension force. Actually, go ahead and box all of these maybe, because these are our final answers. But if I were to look at the actual forces in that beam at that point, I would have a, let's see, an outward force, a axial force of 5√3 kips, a positive shear, which in this case, because it's on the right-hand side of the element, is downward. So that would be 5/3 kips. And a positive moment, which because this is on the right-hand side of an element, is counterclockwise, MA of 10 kip feet. And those are all of the internal forces that are present on the outside, or not on the outside, all the internal forces that are present in the member at point A. And later we'll learn that these internal forces are very important. And the reason for this, well, you'll especially see this when you get to mechanics and materials, these internal forces are what you then use to actually design your cross section. So in statics, we tend to focus on actually teaching you how to get these internal forces, but then in later courses, you'll actually learn how to apply these to the design of individual members. So for example, reinforced concrete or steel design, you'll use these forces and once you have those forces, you'll often use statics to get the forces or more advanced techniques to get the internal forces. But then once you have them, you'll use the various things you learn in upper level coursework to actually learn how to design a cross section. What I mean by that is, okay, well, how big it is it? How wide should it be? How thick should it be? How strong should the steel or concrete be? All of these types of things. All of these are going to be dependent on the actual internal forces you calculate. All right, for this next example, I want to work through a similar beam, a simply supported beam, but in this one, I want to consider how to find the internal forces when the external load is a continuous or distributed load rather than just a simple point load. Example 2, let's do a beam with a point load, or sorry, beam with a distributed load. A beam with a distributed load. So let's consider this. Now I'm going to have a beam, and I'm going to make this simply supported just like before, keep it nice and simple. And the method's going to be generally the same, except it's going to be a little bit more complex because we're dealing with this simple load here. We're dealing with the more complex loading, I should say. Now, let's say we have a triangular wouldn't be too bad, or a constant load wouldn't be too bad, but let's make the loading really fun and make it trapezoidal. So something like this here. Oh, wrong direction. Let's say on this side of the beam, let's see, I guess I did the last one in English, I'll do this one in metric. Let's say this is 5 kilonewtons per meter down here, or actually let's make it 2 kilonewtons per meter. And then up here, this one can be, I don't know, maybe 8 kilonewtons per meter. So I have a load that starts out at 8 kilonewtons per meter, and it decreases down linearly to 2 kilonewtons per meter. Like so, and like so. Then, so there's that, and this is given. So all this is given. Oh, we would also need to be given the dimension of this. And let's just come up with some dimensions. Let's say this is, what do I want to do? Maybe 12 meters long. So rather decently long beam. It'd be a very beefy beam when you actually design that thing. 12 meters, that's a pretty good span. Anyway, let's not get worried too much about that. And then let's say we have a point, let's see, I'll go ahead and call this point A, this point B, and maybe have some point C, which is, I don't know. What might I want to do? I already did 1/3 last time. Maybe this is going to be 3 feet. So maybe I'll make, or not 3 meters. So maybe I'll make this 3 meters and this 9 meters. That looks good. So what I want to do is, I want to find find the internal forces at point C. And this one's going to be a little bit trickier. The internal forces at point C. The internal forces at point C. All right, so let's go ahead and work through this. And the steps are really going to be exactly the same. We're going to start by finding the external reactions, the reaction forces at A and at B in this case. So the first step will be to find the external reaction forces. Find external reactions. And so how do I do that? Well, as we may remember from previous discussions of distributed loads and such, we can do one little trick when solving for external forces. We can replace distributed loads with equivalent point loads. So we can only do that though when solving for external loads. When we actually get later to functions, we won't be able to do that for the actual load functions and things like that, but we'll see that later. For now, we're going to use the method of replacing things with equivalent point loads. Replace distributed load. You can replace the distributed load with equivalent point load. With the equivalent point load. So we have this here. Now let's see. First of all, I want to look at this loading and see how I can sort of chop this up a bit. I'm not going to draw this to scale for simplicity. Well, let's see. So we're going to have this end here and this end here. This is at 2 and this is at 8. And basically, if I can manage to draw a straight line-ish here, I'll straighten enough. Straight enough here. What we basically have in this trapezoidal loading is a triangle and a rectangle. And the dimensions of this rectangle are 2, a width of 2, and a length of 12. Basically, again, we essentially analyze these using geometric methods, even though, of course, these aren't really actual shapes, they're loadings. We can use the equations from geometry to analyze these. So what we really have is a rectangle with a height of 2, and then we have a triangle with a height of 6. 2 plus 6 being 8. And so I'm going to replace these with 2 equivalent point loads. The first will be will be equal to the area of the rectangle. So that's 2 kips per foot, 2 kilonewtons per meter times the length of 12 meters, which will be 24 kilonewtons. 24 kilonewtons. Actually, I think I might need to make this a little bigger. 24 kilonewtons. So I have the 24 kilonewton point load, and that again is the equivalent point load of the rectangular portion of that load. 24 kilonewtons. And then I have the equivalent point load of the triangle, and the area of a triangle is 1/2 base times height, so that is basically 1/2 6, or 1/2 times 6 times 12, or 6 times 6, or 36. 36 kilonewtons. Now, in terms of dimensions on this, remember, we can replace distributed loads with their equivalent point loads, and so the magnitudes are easy enough. You just find the area of the geometric shape. But what about where you place them? Well, where you place them is you put them wherever the centroid of that load is. So you have a centroid here, or the triangle, for example, will have a centroid 1/3 from its base, which means the centroid of the triangle portion of the load is 1/3 the way along the beam, which means this is going to be 4 meters. Again, the centroid of a triangle is 1/3 from its base, and so that means the centroid of this loading is right at the centroid of the triangle, and so, again, 1/3 of the entire length of the beam, or the length of the triangular loading is, or the entire beam length or the entire load length are 12 meters, and 1/3 of that will be 4 meters. Then the centroid of the rectangle, that's very simple, that's just right in the middle. That would be 6 meters from the left, which means since we're already 4 meters here, we would need just an additional 2 meters here. And that will help us locate our loads, or that will allow us to firmly locate where the centroids of our equivalent point loads are. And again, we're doing this just for the sake of finding the external reactions. If you're doing load functions, you can't necessarily use these. Use that equivalent point load method, at least past the stage of just finding the reaction forces. So then we're going to have an AY, an AX, and then a BY here. So I'll go ahead and get these. And you know what? I could go ahead and solve for BY, but I'm gonna for our sake here, I think I'm actually just gonna work with the right-hand side of the beam. So I don't really see a need to get the BY since we're not even gonna use it for this problem. So I'm just gonna be kind of lazy and only get AY. And I'm gonna do that by taking the sum of moments about point B. Sum of moments about point B. And so I will have basically just 3 moments here. And I don't have to worry about AX either because it's clearly going to be 0. I can just say sum of forces in the x direction equals AX, and that's just equal to 0. AX is equal to 0. There are no horizontal loads applied to this beam, so our horizontal reaction force at A is going to be 0. Then, so MB, I'm going to take the sum of moments about point B. I have AY, which will be a negative moment, because clockwise rotation about point B, times a moment arm length of 12 meters. Then the 36 kilonewtons, both of these are going to be positive because counterclockwise rotation about point B, plus 36 kilonewtons times a distance or a moment arm length of 8 meters, plus 24 kilonewtons times a moment arm length of 6 meters. And all of this is equal to 0. And if I go and throw that into my calculator and move everything over to that other side, move 36, so 36 times 8 plus 24 times 6, let's see, 36 times 8 plus 24 times 6, and divided by 12, I will get 36 kilonewtons. I found that AY is equal to 36 kilonewtons. Well, actually, if I really want BY, I can just do a sum of forces in the vertical direction now. That would show us that BY would have to be equal to 24 kilonewtons. But again, all we're going to need is AY for our problem, because what we're trying to find is we're trying to find the again the moment at point C, which is 3 meters from the left. Now this is going to be quite a little bit trickier than the previous one, so this is where the problem gets interesting. 2. Draw a free body diagram of cut section. So we have our beam here. I'm just going to draw this as a line element. And we will have a, let's see, that is a 36 kilonewton force at the left-hand side. A 36 kilonewton force on the left-hand side. Then, I'm just going to go ahead and assume positive everything. So this is point C, so I have a CX, or sorry, an NC. And then a downward, but positive VC, assuming positive shear. And then I'll go ahead and assume a positive moment as well, and MC. Now, I have my trapezoidal loading, and we start here at 8 kilonewtons per meter. And to actually get these, we can apply the same equivalent point load method, but immediately we have a problem. And that is, we don't know this left-hand height yet. We don't yet know that left-hand height. So we have to go and do something that we're always sometimes loath to do, and that is go back to basic trigonometry. Oh no, not basic trigonometry. Anything but basic trigonometry. Don't make me do geometric proofs again. Oh no. Oh, that'd be a fun thing on an exam. We could have like, just a random problem on an exam question. Just, prove this trigonometric formula or prove this trig identity. It'd be oh so much fun, but okay. Maybe not appropriate for statics class. I think I've traumatized you, my poor students, enough this semester. Okay, so basically what I want to do is, before I can solve for these, I guess I could say NC is equal to 0, that's easy enough, but I need to solve for, before I can find where, apply the centroid of the, before I can find the size of the rectangular portion and the size of the triangular portion, I need to actually know what this height is. Without knowing that, I can't do anything. So I need the height from here to here. So how can I do that? Well, I have a few ways. Later on when we get to shear moment functions, we will actually find an equation for the W as a function of X, the distributed load as a function of X. But for now, since we're not dealing with continuous loading yet, or not actually, sorry, not finding the internal forces at any point, not at any given point, like we're solving for, I should say, currently we are solving for the internal forces at a specific point. Later on, we'll learn how to find them as functions of X. But for now, I think the easiest way is to apply some basic trigonometry to this problem. So consider the load. Basically what we have is, if we look at this global portion, we effectively have a triangle that is, maybe I'll draw it over here just so you can see what I'm thinking about here. We have this triangle, and it's kind of like this. Well, it's a trapezoid, of course, but we're going to look at the triangular portion. This is 2, and this is 8, so definitely not to scale here. Or I should actually say this is 2, and this is 6. And this height, this dimension here is 12. However, we are interested in the height on this portion here, and this is 3 meters, and that would be 9 meters now. So all we're really interested in is that what we need to find right now is this height here. And to do that, we can actually apply, we can simply apply similar triangles. Consider this triangle here. Consider this triangle here. Let's call this X. So yeah, we are basically back at grade school trigonometry here. So we have 3 here. So basically I have 2 triangles. Now you can probably jump ahead if you're getting bored with basic trig. But this is a refresher and things. But again, it can be a little counterintuitive because we're not actually dealing with physical objects here. We're dealing with a diagram in terms of, describing the loading per linear length, like kips per foot or kilonewtons per meter or something. But you can actually analyze them with the exact same things, tools and techniques you would any geometric shape. And so you have one triangle that has a height of X here, which is basically this height here, and then a length of 3. And we have the bigger triangle, this one here, this triangle here, and that has dimensions, let's see, of 6 and 12. 6 and 12. And I know by basic properties of right triangles, if I take one right triangle within another right triangle, because this angle is the same as this angle, these 2 triangles are similar, or I could say they're proportional to each other. So I could then say x over 3 is equal to 6 over 12. So that means that x is equal to what? That's going to be, let's see, that is going to be 1/2. That's going to be, does that make sense? X over 3 is equal to 6 over 12. Yeah, that should make sense. So then this is going to be, if I multiply this by 3, that will be 6 times 3 divided by 12. Okay, sorry, not 1/2, but 1.5. That makes a little more sense. That makes me happy. That is 1.5, and this would actually be in newtons of in units of kilonewtons. So 1.5 kilonewtons, which means I then have a diagram like this. I again have a triangular section and a rectangular section, except their triangular section will have a height of 1.5 kilonewtons, and then this one here, well, the rectangle, have a height of 8 minus 1.5, which is going to be 6.5 kilonewtons. And now we have something we can actually solve for. So we can use the equivalent point method again, but again, we can only use that when we're looking for the loads at a particular point, or the internal forces at a particular point, or the external forces at a particular point. The moment you start solving for anything as functions of x, then you do actually have to you can't use the equivalent point load method anymore. So you have so let's go ahead and draw this as, again, I'm going to go ahead and draw this as replacing this with 2 equivalent point loads. And I'm going to go ahead and draw it a little bit longer because I want to have a lot of room for this. So first I have my, well, first I can just say sum of forces in the x direction Sum of forces in the x direction means that NC, the normal force here, is equal to 0. So that's easy enough. So I don't have to worry about drawing that even. I have a 36 kilonewton force, reaction force at point A. Then I have a downward VC and some, again, counterclockwise but positive because of where it is on the beam, internal force MC. Now I'm going to have two equivalent point loads. The first is going to be from the triangular portion. And I know that it's going to be 1/3 the length of the triangle, or simply 1 meter from the left-hand side. So this triangle has a length of 3 meters, so that means 1/3 of that is 1 meter. And so the magnitude of this is going to be 1/2 base times height, so that is 1.5 times the base, which is 3, times 1/2. 1/2. So that would then be, let's see if I want to do this in exact mode. 1.5 times 3 over 2. I'm feeling a little lazy today. And that's 2.25. I guess I'll just go ahead and do this as decimal for now. This is equal to 2.25 kips. So we have an equivalent point load from the triangular portion equal to 2.25 kips, and it is at a location 1 meter from the left-hand side of the beam. Oops, sorry, not kips. That should be kilonewtons. Keep on wanting to go back to English units. Let me fix that. 2.25, not kips, but kilonewtons. If I wanted to pronounce that in a bizarre way. Kilonewtons. Anyway, stupidity aside, let's then go and find the equivalent point load of the rectangular portion. This is going to be 6.5 kilonewtons, well actually kilonewtons per meter. If I want to actually show the units, you do it like this, times a length of 3 meters. And that should come to 19.5 kilonewtons. 19.5 kilonewtons, so 6.5 times 3. And it does indeed come to 19.5 kilonewtons. Now, as far as where this is, again, this is going to be in the center of my beam because it's a constant uniform downward load. And that means 3 meters from the left, or since the overall length is 3 meters, that would be halfway down, or 1.5. And since we already have 1 here, a length of 1 here, we would need an additional 0.5 or half a meter to get to that location there. 0.5 meters, and then this length here is 1.5 meters as well. All right, so I guess I can go ahead and apply equilibrium to solve for VC and MC. So the first one, I can do a summation of forces in the vertical direction. Oh, if I can keep from jumping ahead, I can do a summation of forces in the vertical direction. And I'll have an upward 36 kilonewtons, a downward 2.25 kilonewtons, so minus 2.25 kilonewtons, minus 19.5 kilonewtons, and then minus a VC. And all of this is equal to 0. And so therefore, VC is equal to 36. Well, actually, let's see here. Well, no, I can just imagine bringing VC over here and then flipping the equations. That's fine. So I would have VC is equal to 36 minus 2.25 minus 19.5. And if I throw that in my calculator because I'm feeling lazy and don't want to do mental math right now, 36 minus 2.25 minus 19.5, and I get 14.25 kilonewtons. And that is going to be positive shear there. 14.25 kilonewtons, and this is positive shear. Next, I can do a summation of moments about point C to get the moment at C. And again, I'm doing it at point C because I don't want that VC to have any influence on the moment calculation. Again, it's not so important for this type of simple calculation, but later when we're getting VC in terms as a function of x, that will be very useful. So it's good to get in the habit of it now. So I'll have negative 36 kilonewtons is going to generate a negative moment because clockwise rotation about point C. So negative 36 kilonewtons times a moment arm length of 3 meters. Then these two are going to be positive. The two equivalent point loads will generate positive moment about point C. So plus 2.25 kilonewtons times a moment arm length of 2 meters. Then, again, 0.5 plus 1.5 produces 2 meters. Then plus the 19.5 kilonewtons times a moment arm length of 1.5 meters. And this then comes to 0. Oh, I'm forgetting one crucial thing, and that is my MC. And it's plus MC, not because I assumed it to be positive, but because on this diagram it is counterclockwise. And so MC there. MC will then come to 36 times 3 minus 2.25 times 2 minus 19.5 times 1.5. And that will then come to, let's see, 36 times 3 minus 2.25 times 2 minus 19.5 times 1.5. And if I mathed all that correctly, this will come to 24.25 kilonewton meters. Uh, 24.25, or actually, sorry, not 24.25, 74.25. 74.25 kilonewton meters. So if I were then to go and draw this out, if I were to look at the actual forces at that cut, I could say they have forces like this. Ignoring, I'm just cutting out at a small differential element or something. In fact, maybe I could actually label this on differential element. If I were to take a differential element right at that cut, like a small dx here, what I would have, again, if I take a small dx small enough, this is point C here, if I take a small slice of small dx small enough at point C that we can neglect the difference between the left and the right, I would basically have a downward shear arrow of, let's see, that would be 14.25 kilonewtons, and upward on the left of also 14.25, this being the state of positive shear. Then I would have positive moment on both sides. Well, positive state of moment, I should say, but a clockwise arrow on the right and or on the left, and a counterclockwise on the right. And this would be 74.25 kilonewton meters. And the same here, 74.25 kilonewton meters. And that would be how we can find the distributed, or how that would be an example of how we can solve for internal forces on a member with distributed loadings. For our final example in this portion of the lecture, I would like to look at finding the internal forces in a slanted or a diagonal member. So example 3, we will look at a diagonal member. Or I should probably say an inclined member. How do we calculate the internal forces in an inclined member? And I don't know if I need to work all the way through this one, but we'll take a look at this. So let's say we have something like this. Let's say we have a member, and I'll go ahead and make it simply supported. And then we work through this one all the way or not, just depending on, what I feel we need to do. So say we have this here, and for simplicity, I'm just going to put a single load in the middle here. We could have a case where you have both a distributed load and an inclined member, but here I'll just say there's just an inclined member with a single point load applied somewhere. So let's say this is a 5 kip load, and let's see here. Well, actually, I think I'm going to make this be a 3, 4, 5, so maybe I'll make this be an 8 kip load. And in terms of the slant of this thing, this is going to be a 3, 4, 5. I'm going to let this be a 3, 4, 5 angle. So 3, 4, and 5. The beam itself is slanted that way. And I'm going to say this is a pin here and a roller here. And really, I think that should do it. Oh, I guess we'll stay with this. We still need the length, so let's go ahead and get that. Let's say this is applied, I don't know. Now I'm going to go ahead and give the dimensions in terms of the length of the beam. Let's see, like this. Here and here and here. And then this looks right halfway down the middle, but I think that's too boring. So let's say this is, maybe 4 feet and 8 feet. 4 feet and 8 feet. So something similar to the first one where it was 1/3, or we were looking at 1/3 and things like that. Or yeah, the equal 3 divisions and that kind of thing. Actually, maybe I'll do exactly that kind of thing. Let's say we have a 4 feet here and 4 feet here, and I'm going to find the loadings at point C here. Maybe this will be point C, and this will be point D, and this will be point A, and this will be point B. So given, and then find the internal forces at point C, or sorry, at point D. At point D. So I want to find the internal forces at point D. Now, how do we do this? Well, the thing we need to keep in mind, or the thing we need to realize, is that shear and moment are all about the member's local axis. Are all about the member's local axis. Or not, maybe I shouldn't say all about, but all relative to the member's local axis. And I should probably also say axial force, shear, and moment. Axial force, shear, and moment are all relative to the member's local axis. Again, if I say, again, relative to the member's local axis, so shear does not mean upward or downward force. Fundamentally, it doesn't mean that. In this case, in all the previous cases we've looked at, we've been dealing with horizontal beams. And so it's very easy to think, oh, shear, that must be an upward force. But really, that's not true. Or you may think axial forces in these two beams, they're horizontal, so the axial force is also horizontal. So it's easy to think, oh, axial force means a horizontal force. That is not the case. Axial force means along the axis of the beam, along the length of the beam. Shear means perpendicular to the beam. So every one of these things is going to be analyzed along the member's local reference frame. And so to do that, what I want to do is I want to convert any loads into components that are along the member's local axis. I really need to do that. So we need to apply a little trigonometry in order to get this along the member's local axis. So I need to apply a little trig to break this into basically a component that is parallel and a component that is perpendicular. Let's see, parallel and perpendicular. So we have a couple different ways we can do this. Let's, sometimes I have to bang my head against the wall there if I haven't done this in a while to recall how to do this. Let's walk through the trigonometry. Let's draw a few triangles and figure out how to do that. So again, so we know that the beam itself is at a 345 angle. So basically we want to break this into a component that is, we're putting it in the member's local coordinate system effectively. So let's think about that. Basically, let's think about this. So I'm going to draw this load, and we have this 8 kip load, and it's going to have some component that is parallel. So we have a, maybe I could call this F parallel to the beam, and, or actually maybe I could call that an Fy. Actually probably an Fx because it would be along the x-axis of the member, and then an Fy, like this. And basically I'm defining this as my x-axis and this as my y-axis. I usually try to, even for slanted beams, I try to keep my 0 point at the left-hand side. So in this case, if we look at this, Fy would actually be negative. Okay, and this is a right angle, and that's a right angle there. So what else do we know? Well, let's think about this more. Let's see. This would be a lot easier if we're dealing with in terms of angles. Let me draw this a little bit bigger because this is going to be hard to draw other things on. So we have 8 kips, and then we have components. Maybe I'll try to draw it a little bit more realistic here. A right angle like this. So we have our 8 kip. Oh, it's not, we're looking quite right. Still not quite there. Okay, 8 kips, and then this is a right angle, and this is my Fy, and this is our Fx. Okay, so we need to find a way to convert this 345 into that. Now, basically, I know that this Fx off the horizontal is a 345. So I can say that this is a ratio of 3 to 4 to 5. And let's see, how does that help us? 3, 4, 5. Well, this would be a lot easier if these I usually think in terms of angles a little bit better. So let me just go ahead and get the angle, and then we can think about how to get that in terms of ratios. So I think of this theta here, that would be the inverse tangent. Here, let's see, this is the inverse tangent of 4/3. Inverse tangent of 4/3, and that's going to be 53.13 degrees. 53.13 degrees, and which means this angle from here to here is 90 minus that, which will be 36.87 degrees. 36.87 degrees, and that means this here, this angle here, is going to be, that will be, again, well, it'll be 90 minus that, so back to 53.13 degrees. And there's probably a more elegant method to get this trigonometry. And so then I can just say, okay, well, probably could have recalled some basic physics with balls and ramps and things like that, blocks and ramps. Oh, blocks and ramps. So I can then say that, let's see here, that actually, yeah, the same rule with blocks and ramps applies, where it's the horizontal is the sine, so that makes sense. So here, then, let's see, I could say that the sine of 53.13 degrees is equal to Fx, opposite over hypotenuse, is equal to Fx over 8, Fx over 8, which means that Fx, the x component, is 8 times the sine of 53.13 degrees times the sine of 53.13 degrees. And the sine of 53.13 degrees is just 4 over 5, opposite over hypotenuse. So that is 8 times 4 over 5, which is, let's see, let's just do that in decimal mode, 32 over 5, and that comes to 6.4 kips. 6.4 kips. And then the, let's say the Fy is going to be equal to 8 times the cosine of 53.13 degrees, which is 8 times 3 over 5. Again, the cosine of 53.13 is just 3 over 5. So that would be then 24 divided by 5, which comes to, not 324 divided by 5, 24 over 5, which comes to 4.8 kips. 4.8 kips. So basically what we have then is, we have divided this into a parallel and perpendicular component relative to the beam. So this is 4.8 kips, and this is 6.4 kips. So I divided this into parallel and perpendicular components. Now, at this point, when all I'm trying to do is solve for internal number forces, I never have to worry about the angle again. Once you've broken up all the forces into parallel and perpendicular components, you never need to worry about the angle itself again. So I can then analyze a beam that's like this. The beam, I shouldn't just say like this, I should say in its local coordinate system. So I've taken the load that was downward, but I have now transformed it along the beam's local axis. So now I have a beam like this, a simply supported beam, and the beam is now nice and horizontal again. And I'm going to have the let's see, relative to this, the Fy is downward and the Fx is to the left. So I would have a force like this, and a force like this, and the Fx is going to be 6.4 kips and the Fy will be 4.8. So 6.4 kips and 4.8 kips. And then we're looking for the load, or the forces I should say, at point D here, I believe. At point D, and the dimensions here are 4 feet, 4 feet, and 4 feet. And we would have a y and an ax. In this case, ax would not be equal to 0. And we would have a by here. And we have a by. And once we have this, well, I want the dimensions. Let's see, that's 4 feet, 4 feet, and 4 feet. And then once you have this, it really is cake. The hard part is just getting, for this type of thing, for a slanted beam, it's just getting this set up. And so once you have that, the rest really isn't too bad. Setting this up, again, setting this up is the hard part. Once all loads are transformed to be along the member local axis, to be along the local axes, we will proceed as you did in example 1. Proceed as in example 1. Or just repeat steps from example 1. And the basic steps are, as a review, 1, apply global equilibrium, or apply global equilibrium to get reaction forces, to find external reactions, 2, cut the member at the chosen point. At chosen point, revealing internal forces. And then 3, apply equilibrium again to get internal forces. To find internal forces. And that is the basic method. Now, this could be quite complex. These can get quite complex. So, for example, imagine if you had a distributed load that was on say a downward distributed load also on a slanted beam. Well, that would be quite challenging, because you'd have a distributed load. You'd have some distributed load along the axis of the member and some not along the axis of the member, and that could be a little bit tricky. But really not too bad once you've gotten the hang of it. So, I think that'll do it for this portion of the lecture. I think I'm going to put out a very brief part 3 where we look at how you can apply this to basic frames. But for now, I think that'll do it for now. And just on this portion of the lecture, all I wanted to do was go through some examples and explore some of the methods and some of the mathematical tools that you have to use, such as the handling distributed loads and such, of finding the internal forces on members when those members are subject to axial force, where they're subject to axial force or horizontal loading or vertical loading, and to find the internal forces, of course, which are of course axial force, shear, and moment. All right, please let me know if you have any questions. I will see you soon for part 3. I hope you've learned a few things in this. Let me know if you have any questions again, either here on YouTube or in class. That'll do it for now, and as always, thank you.